Hello everybody. Today we are going to talk about battery recycling. This is the interesting topic I would like to share with you. Here, let's look at the presentation. Battery recycling. I'm going to share information regarding battery recycling and how we can carry out research will be outlined today. Definition of recycling. Recycling is processing used materials into new products to prevent waste of potentially useful materials, to reduce the consumption of fresh raw materials, reduce energy usage, reduce air pollution and water pollution by reducing the need for conventional waste disposal, and lower greenhouse gas emissions as compared to virgin production. Why recycling is important? There are various reasons, but most important reasons are economical reasons and environmental reasons, because nature resources are getting lower and lower. So from economical point of view, it should be gone into recycling economical loop. And from the environmental reasons, they can harmful both human beings and also animals and vegetables, so fauna and flora. And this is the reason waste material should be recycled. What is recycling? The reuse and remanufacture of waste materials. What is the purpose of recycling? To recover useful materials and save resources, and to prevent pollutants reaching the waste stream. This is the important. What are the benefits of recycling? More efficient resource use, lower energy consumption, and reduce pollution. This is for these reasons, recycling plays a vital role in our daily life, in our life. On-site recycling or in-situ recycling benefits close to the point of generation, because there is no transportation, less contamination, lower cost raw materials, reduced waste disposal costs. And let's look at the cost. Capital investment in equipment, staff training, maintenance and repair, staff time, residue disposal, and quality control. There are various recycling technologies. I'd like to mention each of them. The first one is activated carbon adsorption. Mainly organic containing waste and reactive waste can be treated by this method. Distillation is another recycling technology, and halogenated solvents and non-halogenated solvents and other organic waste and liquid solution can be treated by this distillation process. Steam distillation is the same as distillation. Halogenated solvents, non-halogenated solvents, and other organic waste can be treated by this method. And electrolytic recovery, metal-containing wastes can be treated by this method. Further, we are going to look deeply into this electrolytic recovery. And when we look at the ion exchange, it could be used for corrosive waste, and metal-containing wastes can be applied successfully, like activated carbon adsorption. Hydrometallurgical concentration can be used for metal-containing wastes. Membrane separation is frequently heard technology. Oil-containing waste, metal-containing waste, organic-containing waste can be treated by this method. Evaporation is another recycling technology. You evaporate the solution, like halogenated solvents, non-halogenated solvents, and other organic waste can be treated by this method. Another interesting recycling technology, freeze crystallization. Based on the freezing point of materials, various materials can be treated by this method. Let me give you an example. Corrosive bases, halogenated solvents, non-halogenated solvents, other organic waste, and metal containing wastes, and organic containing waste can be treated by this method. Another recycling technology is the pyrometallurgy. And metal containing waste can be treated by this hydrometallurgy. By pyrometallurgy. Pyro means fire. Metallurgy is the extraction of various materials, and using the pyrometallurgical process, it is possible to recover most metals, most metal-containing materials. A study case here will be outlined. Battery recycling. The paste, if a battery containing waste containing material is called paste, is subject to the leaching process. After the leaching, residue washing and inert residues are obtained. Inert residues means we cannot leach this kind of materials. This is inert, okay, unreactive. And residue washing goes to purification or refining processes. And after the refining processes, for example, bismuth, copper, arsenic, antimony goes another side. On the other hand, lead goes to electrowinning. After the electrowinning, lead can be recovered, lead can be produced by this electrowinning process, melting and casting, and then we can produce 99.99% lead ingots. And this is 49 lead can be produced by this method. This is placid process. I'd like to mention about the case study which I 10 years or 15 years ago carried out. Silver recovery from spent silver oxide button cells. What is button cells? I'd like to mention. Button cells were developed to miniaturize battery packs and to solve stacking problems. So teeny tiny small cells is called button cells. These cells have a high capacity per unit weight and a long operating life and are currently used in hearing aids, digital thermometers, insulin pumps, portable medical monitors, hospital pagers, watches, toys, and calculators. This kind of materials frequently use silver containing button cells due to high capacity per unit weight and long operating life. While battery is in use, the silver oxide is reduced to metallic silver and the zinc metal is converted to zinc oxide. The overall reaction is given by silver oxide in solid form plus zinc metallic form goes to silver and zinc oxide. By charging, the reverse reaction takes place. To silver plus zinc oxide goes to silver oxide and zinc. Let me write down something for you. Anyway, I cannot do that. Here, the first one is, as you see, Mercury distillation furnace. Mercury is, to a certain extent, is used in teeny tiny small miniature batteries, button cells. And it needs to, first of all, distilled. And then this distilled mercury should be subjected to or fed to mercury condenser. And then 5,9 or 4,9 mercury can be obtained by this simple distillation and condensation process. Here, Mercury containing waste sludge is subject to the mercury distillation furnace, as you see here, and is subject to the post combustion, and waste gas are generated. Here are treated by wet cleaning technology. Here is a mercury settling tank, and acidic wastewater also treated. Alkaline wastewater can also be treated. As you see here, activated carbon filter can separate polymer-based materials or any other mercury-based material can be treated by using activated carbon filter. It can filter almost anything. Very successful, actually. Here is the example of mercury-containing waste or mercury-containing battery treatment in battery recycling plant. Mercury is a heavy metal and dangerous metal, hazardous metal. It's recovered from spent silver oxide bottle batteries by distillation. After the mercury is removed from the system, silver and other fractions are leached using nitric acid. You know, nitric acid can dissolve quite easily silver and other metals. And silver chloride is then precipitated from this solution. You would probably remember from the chemical metallurgy laboratory, silver nitrate is treated with sodium chloride or potassium chloride to precipitate silver chloride. You would remember vividly. And silver chloride is then precipitated from this solution by employing sodium chloride. So silver chloride is obtained in this process, is then subjected to reduction to metallic silver by employing sodium hydroxide and dextrose. Dextrose is carbon-containing material. It can make sure silver oxide turns into metallic elemental silver. Silver chloride reacts with sodium hydroxide to form silver oxide, and silver oxide finally turned into elemental silver, metallic silver. Here is the reaction: dissolution of silver in nitric acid media. 3 silver plus 4 nitric acid goes to 3 silver nitrate and 2 water and nitrogen oxide. Or it could be excited by NOx. It could be nitrogen dioxide or nitrogen monoxide. If it is in the form of silver oxide, quite easily dissolved in nitric acid, easier than that of silver. Silver oxide reacts with nitric acid to form silver nitrate and water, as you see here. The composition of Maxwell SR1220SW silver oxide bottle cell. For this research program, we use this Maxwell silver oxide bottle cells. Here are the components: steel case, 55.25 weight percent. Battery phase 37.1 weight percent. Membrane and plastic 4.25 weight percent. Electrolyte 3.1, and remainder is 0.3 weight percent. And when we look at the chemical composition of the cell powder, it is also called paste, battery paste. It contains 62.09 silver, 13.55 zinc, 0.54 mercury. As you see, mercury is used to suppress hydrogen evolution in this miniature battery packs. And carbon 2.48. Carbon can be used as anode paste material. And sulfur, iron, lead also is found in to a certain degree in cell powder. Cadmium and nickel metals are not detected in this kind of battery system. Spent silver oxide bottle cell is subject to crushing, drying, and grinding, and we will get raw cell paste. Sieving, homogenization is subject to, after that we'll get cell powder. Based on this cell powder, we carried our research program. And the dissolution of cell powder in nitric acid media at various acidic concentration modalities. And we will get silver nitrate and other metal nitrates. Precipitation by potassium chloride instead of potassium chloride. It is also possible to employ lithium chloride, sodium chloride, etc. The bottom line is here to provide the solution with chlorine ion. Doesn't matter which chloride. It could be silver, it could be sodium, potassium, lithium, or ammonium chloride. Doesn't matter. The important thing to supply chlorine ion into aqueous solution. And wherever we get silver chloride, and when we add small amount of hydrochloric acid to make sure the media is the media is acidic, and hydrochloric acid has no action on silver, so you can successfully use this hydrochloric acid. And zinc, is an active metal. There's a replacement reaction or cementation reaction. We talk about the chemical metallurgical laboratory. The silver chloride reacts with zinc to form zinc chloride and elemental silver. And this is the flow chart for the silver recovery from spent silver oxide bottom cells. Leaching efficiency can be calculated using this formula, MT over W times M0 times 100 gives the percent leaching efficiency. W is the weight of the cell powder taken for each experiment. MO is the silver content of the cell powder or battery paste. MT is the silver quantity at the end of the leaching process. How there would be a question regarding how would you determine MT? After the reaction, the obtained silver is dissolved in nitric acid and titration process is carried out. And using potassium chloride, we can titrate silver nitrate, and this is the way we can establish the amount of silver present in the solution, and we can, using this value, we can calculate our leaching efficiency. This is a research program and the effect of nitric acid molarity on the dissolution of silver depending on quantity of the cell powder. Here are the conditions. The reaction takes place in 1 hour and the temperature 25 Celsius, 5 cc solution and 200 RPM is used. This is the in the y-axis, as you see here, dissolution percentage, and here is the quantity of cell powder expressed in milligram. When we increase the molarity of the solution, and the efficiency increases up to, to 200, up to 100%. And on the other, when we use 0.5 molar nitric acid solution, and based on the quantity of cell powder, dissolution efficiency decreases because we can conclude that the amount of nitric acid is not enough to dissolve all the silver away from the solution. You cannot leach all the silver containing material into the solution. So there should be an optimum point. Let's look at another figure. The effect of temperature on the dissolution of silver. Here is the conditions: 1 hour, 5 cc solution, and the solution is 0.5 molar nitric acid and 2 RPM. When we employ 25 Celsius, we get about 50%. On the other hand, when we increase the temperature from 25 to 65 Celsius, here more than 90% dissolution efficiency is obtained. And we can, it is safe for us to express that temperature plays a vital role in this dissolution reaction, as is indicated in scientific literature. As you see, when we increase the temperature from 25 to 35, it goes to 60%, and from 35 to 45, it goes to 80%. On the other hand, when we increase quantity of cell powder from 50 milligram to 250 milligram, and dissolution efficiency decreases, we can quite easily conclude that the amount of nitric acid is not enough to dissolve all the silver from this material. And you should remember that the battery material contains both silver as elemental form and silver oxide. When discharging the battery, silver oxide turns into, by the help of zinc, turns into silver. And by the charging, the silver turns into or converted into silver oxide. And then charging takes place. So what I'm saying is here, this material both contain silver and silver oxide. This is a solution percentage here, quantity of. When we increase the molarity of the solution from 0.5 molar nitric acid to 1 molar nitric acid, we can observe effect of temperature on the dissolution of silver. When we look at 25 Celsius, it is lower than actually 80%, and it goes to higher than 80%. On the other hand, when we increase temperature up to 45 Celsius, almost 100% dissolution efficiency is obtained. Again, I'd like to mention that the temperature plays a vital role in this kind of dissolution experiments. Also, in cementation reaction or replacement reaction, temperature plays a vital role, an important role. Here, and now let's look at the effect of molarity of the solution. When you supply more nitric acid, and you can guess that the dissolution efficiency increases, and this is the effect of time on the dissolution of silver. When you set the duration of 15 minutes, you in the employment of 0.5 molar, lower than 40%. But when you increase the time to 60 minutes, and it exceeds 40%. But when we increase both time and the molarity of the solution, almost 100% efficiency is obtained. This is the research program. We need to establish each parameter's effect, and then we are going to conclude. We are going to establish optimum parameters for the dissolution process and also obtaining process recovery processes. And step by step, we are investigating each parameter, and we set constant other parameters. In this research program, in this graph, we can also observe effect of time and effect of molarity. And the time, the amount of solution, 5 milliliter, and the weight of the waste material, 50 milligram, is set to constant, and temperature is room temperature, 25 Celsius. Let's look at the effect of shaking rate on the dissolution of silver. When we employ literally no shaking, which is 10 RPM, very low, and the efficiency is about 40%. When we increase to the shaking rate to 100 RPM or 200 RPM, and the dissolution efficiency increases from 40% to 60%, from 60% to almost 80%. Okay, and so we can conclude that shaking or agitation rate plays an important role in this kind of dissolution. Especially, we are going to look at the kinetics of this process. It is diffusion-based processes. The effect of shaking rate plays a more important role in this dissolution processes. Here is the plot of 1 minus x over 1 over 3 with respect to time, and each temperature we can calculate K value. In the kinetics calculation, we can use this model. This is shrinking core model in the kinetics, dissolving kinetics, and each slope gives us L and K values. Each slope gives us K value, and from this L and K value versus inverse temperature gives us the Arrhenius plot of L and K versus 1000 over temperature, gives us the activation energy of this process. Okay, now we need to convert silver chloride to silver. There are various methods, ladies and gentlemen. Okay, there are various, because silver is a precious metal. Silver is a noble metal. From electrochemically speaking, its place is much higher than that of hydrogen gas evolution, and it is arbitrarily chosen as 0 volt. And the reduction potential of silver is 0.8. This is the reason why we call it noble metal. Okay, inert metal, noble metal. Okay, and it's not easily corroded under ambient conditions, or at an elevated temperature. You can use silver-based products, for example. And there are various methods to produce silver. Silver chloride can be reduced to silver by the use of dextrose, by the use of iron metal, by the use of aluminum metal, by the use of zinc. In this specific research program, we employed zinc because initially we used zinc because the material contains zinc, and we continue using zinc metal. But you need to supply this kind of replacement reactions. We need to supply. Just give me a second. Here, let me write down silver chloride plus zinc. We will get zinc chloride in aqueous solution plus metallic silver. This is solid, this is solid, and this is solid. We need to provide a media. It should be acidic media because zinc loves acidic media. And we know that hydrochloric acid has no action on silver. So it is safe to use hydrochloric acid or sulfuric acid. Also, sulfuric acid has no action on silver. And silver chloride can also reduce by aluminum chloride and silver metal. Instead of aluminum, iron could be used. Again, iron chloride and silver, or manganese many base metals can be used for this purpose. Why zinc? Because bottom cell contains silver oxide, silver metal, spent or waste bottom cell contains silver oxide. And let me and zinc metal and zinc oxide. And this is the reason we use for this specific reaction. We preferred zinc because it already contains zinc and zinc oxide. So we can combine all the solution and to treat this solution to get zinc hydroxide. Because, ladies and gentlemen, zinc cannot be discarded. And also zinc is important metal, base metal, and from environmental point of view, from economical point of view, it should be recycled. How we can recycle zinc? Zinc 2 plus reacts with hydroxide, we will get zinc hydroxide. And zinc hydroxide, do you understand what I am saying is here? Why would you use iron, aluminum, or other products? Because it already contains zinc. And this zinc, combine other zinc containing waste solutions, turn into zinc oxide, and this can be used automobile tires. Or zinc oxide reacts with sulfuric acid to form zinc sulfate. This could be used as feed material for animals. And various processes can be employed. So we should be very vigilant, very careful about choosing the right process. And another thing to remember is we need to recover all metals. You remember, sinetten yağ çıkarmak diyorduk. We need to recover all metals, okay? And we need to create a loop from cradle to grave. Each step we need to recover all metals. It could be plastics, it could be metals, organics, ceramic based material, glass, etc. We need to recover all the metals because we run out of natural sources. Okay, let's get back to slides again. Sorry. Let's press F5. Okay, we need to supply media, acidic media. Zinc likes acidic media to run this reaction. Okay, when we use no media, no acid, just distilled water. As you see here, when you use 5 milligram zinc, we always get no conversion efficiency. What is conversion efficiency? Silver chloride is non-metal, is ceramic based material, and we need to create value-added product like silver. When you produce silver, you make money. Now, our purpose is to make money. Okay? We should always remember, we need to make money from economical point of view. When we use 5 milligram, no conversion efficiency, no money. When increased amount of zinc, because you increase the possibility of reaction, increased by the adding more amount of zinc, it is lower than 20%. So there's something wrong. We need to supply, we need to provide hydronamine acidic solution with this media, to this media. And when we use sulfuric acid, also sulfuric acid has no action on silver. It is safe to use sulfuric acid because it cannot dissolve away silver, but it can dissolve away zinc, which is desirable. Or we can use 1 molar hydrochloric acid. And we can quite conclude that when we use 1 molar hydrochloric acid at the amount of 25 milligram zinc, we get almost 100% conversion efficiency. So we conclude that instead of distilled water or instead of 1 molar sulfuric acid, we can employ 1 molar hydrochloric acid. So we can carry out in the further experiment using 1 molar hydrochloric acid. And this is the reason why we use hydrochloric acid. And now in this reaction, we need to establish what is the molarity of the hydrochloric acid. When we use 1 molar hydrochloric acid, and we get more conversion efficiency. So it is, but there is no much difference. I need to mention that there is not much difference between molarity of hydrochloric acid, but based on the results of conversion efficiency of silver chloride to silver, 1 molar is best. So we can continue our experiment based on 1 molar hydrochloric acid. And this is the effect of figure 10 gives us the effect of hydrochloric acid molarity on the conversion of silver chloride to silver. Duration is 1 hour and at room temperature, 5 cc solution of various molarity, acidic molarity, and 200 RPM. The amount of silver chloride is 100 milligram. Mass balance based on 340 pieces of button cells. For this research, 360 pieces of button cells are employed. Total button cells is 353.5 gram. Cell powder amount 131.1 gram. Total silver amount 81.4 gram. And the nitric acid consumption for leaching 165.2 gram. Potassium chloride consumption for precipitation 56.2 gram. Silver chloride amount 101.9 gram. Hydrochloric acid consumption for the replacement reaction of silver chloride plus zinc reaction is lower than 200 gram. Zinc consumption is greater than stoichiometric amount because we need to employ 30% more than stoichiometric amount. And the silver purity is 99.9% final product, and we get 80.4 gram. So almost 100% recycling efficiency is obtained. Total silver amount 81.4 gram, and total silver is 80.4 gram for 360 pieces of button cells. Now, the effect of temperature on the conversion of silver chloride to silver. 1 hour duration, 5 cc solution, and we established that 1 molar hydrochloric acid is the best results, and the 100 milligram silver chloride. We did not change the amount of or the weight of silver chloride. It's set to constant. And when we increase temperature, reaction temperature 25 to 65 Celsius, there is no much difference. So it is wise to use room temperature like 25 Celsius degree. So step by step, we are establishing optimum conditions. Let me remind you of the fact that we use distilled water, it didn't turn out well. We use sulfuric acid, it turns out well, but hydrochloric acid better than sulfuric acid. This is the reason we proceed with hydrochloric acid solution. And we play with some parameters like temperature. When we increase temperature 25 Celsius to 65 Celsius, it didn't turn out much difference. So why would you heat up the solution? There is no point in heating up the solution. Instead, we can stick to use 25 Celsius solution. We can employ this solution. Also, we establish the amount of zinc. When we use 25 Celsius, which is 30% greater than the stoichiometrically needed amount of zinc, because some of the zinc is preferentially reacts with the acidic solution. If you don't use acidic solution, you don't get the results. And this is the reason you need to supply acidic solution, as I explained earlier. Now, the effect of zinc quantity on the conversion of silver chloride to silver. When you use excessive amount of zinc, like 50 milligram or 60 milligram, 100% conversion efficiency is obtained. But our purpose is to establish the optimum value, optimum point. It is something like 25 to 60 milligram zinc is enough to get 100% efficiency. And step by step, ladies and gentlemen, step by step, we are investigating each amount of zinc. When you use, for example, 100 milligram or 1 kilogram, you can always get 100% conversion efficiency, but it's not the point. The point is to establish the optimal results. And this is the reason why we carry out research. When the important thing that we need to characterize the products that we produce during this research program. For example, XRD can be carried out, XRF can be carried out, the TEM, transmission electron microscopy, or scanning electron SEM microscopy can be used to characterize these products. Here are the silver products by the help of replacement reaction with the zinc powder. As you see here, 1200x and 10,000x magnification is, this is a porous structure and the typical pattern of cemented products. Let's come to conclusion. In this present work, a hydrometallurgical process was developed to recover silver metal from spent silver oxide button cells. And the silver metal present in spent button cells could be dissolved more than 99% efficiency with the use of dilute nitric acid solution, 0.5 molar, 1 molar, 1.5 molar, and 2 molar nitric acid solution are tested even under moderate experimental conditions. Even at room temperature, we get successful results. The activation energy of silver distillation was calculated to 26 kilojoule per mole, which indicates that this is an intermediate control process, which means both affected by temperature and agitation or shaking rate. It is intermediate control, means it is between diffusion control process and chemical control process. The dissolved silver was selectively precipitated with potassium chloride solution and silver chloride with an efficiency of more than 99%, ensuring that mercury and zinc remained in the solution. Mercury can be recovered selectively using an appropriate resin. I'd like to mention that this is an important point. Mercury also can be precipitated by potassium chloride solution. But one thing to remember is that if it is the valence is 2, cannot be precipitated by potassium chloride or sodium chloride. If it is the valence is 1, it can be precipitated by potassium chloride and sodium chloride. The important thing I'd like to mention that you need to convert mercury 2 plus. If it is mercury 1 plus, you cannot separate silver from this mercury 1 plus. This is important point. Silver chloride was shown to be reduced to metallic silver by the help of metallic zinc powder in 1 molar hydrochloric acid medium at room temperature at 2200 rpm with an efficiency of more than 99%. Using this method, a fine silver powder with a purity of 99.99% was produced. If you use hydrochloric acid for at room temperature for duration 12 hours or 1 day, 24 hours, you can remove all the zinc from the silver. If you do not use this cleaning process, you cannot get 49 silver. You cannot get 99.99% silver. This is the important thing I'd like to mention. This powder can be used directly in various applications, including the production of silver nitrate, which is used in antibacterial and pharmacological applications, or it could be used in the production of silver cyanide, which is the main component of silver plating bath in jewelry and as an alloying element. Well, let's come to zinc nitrate solution. Zinc nitrate solution from the initial leaching process and zinc chloride solution from the replacement reaction can be put together for zinc precipitation by the help of sodium hydroxide. The proposed process avoids environmental problems and allows for the non-hazardous hydrometallurgic recovery of valuable silver from silver oxide bottom cells. And I'd like to mention that, give me a second. Zinc, or in better pack, zinc oxide reacts with nitric acid to form zinc nitrate. This solution comes from dissolution of battery or leaching of battery. Another solution, zinc chloride, comes from zinc silver chloride and hydrochloric acid plus silver. When we use distilled water, and we'll get low efficiency. This is the reason we need to use acidic media, hydrochloric acid. And hydrochloric acid has no action on silver. This is the reason we can use hydrochloric acid. Instead of hydrochloric acid, here the question arises. Instead of hydrochloric acid, can we use nitric acid? Yes, it is possible. But when we use nitric acid, silver is again dissolved away with nitric acid to form silver nitrate. And this is the reason we use hydrochloric acid, because we optimize the solution. It is safe to use 1 molar hydrochloric acid solution at 25 Celsius. Okay, this is the replacement reaction. When we combine them together, zinc chloride and zinc nitrate, this is valuable solution. And we need to get zinc from this solution. You cannot discard this solution from environmental reasons and economic reasons. When we use sodium hydroxide, we get zinc hydroxide. And in this way, we can produce precious material, valuable product, or value added product. Okay. Thank you for listening. I think that's enough for today. If you have any question, please ask me, or you can drop me email, or you can chat with me. You are more than welcome to ask any question. Okay, do not hesitate. I'm repeating, do not hesitate asking any question. This is important, okay? Regardless of what you think, doesn't matter. Today it may sound for some persons silly, but in 10 years, it's a valuable thought, okay? Don't get scared of asking questions. This is the bottom line. This is the important thing. Okay, thank you very much, all of you. I am ending the meeting. Cheers for